Alright, so we have come to the last two exercises of this section. Let's see what this 19th one has. Here we have two n by n matrices A and B, which are diagonalizable and they commute. That means AB is equal to BA. Then we have to prove that there is another n by n matrix C, which is invertible and for which CA C inverse and CB C inverse are both diagonal. See, being diagonalizable, A and B come with invertible matrices, say E and F, such that again n by n matrices, such that EA E inverse is a diagonal matrix and F inverse is also a diagonal matrix. We can also express this by saying that E diagonalizes A and F diagonalizes B. Now, if A and B commute, then we have to prove that a single matrix does this job simultaneously. That a single invertible matrix can be found which diagonalizes both A and B simultaneously. This is in fact a standard result in linear algebra, which you can find in any good linear algebra book. So instead of solving it, I suggest that you look for this result and its proof. But if you still want to try it yourself, this is a hint. You may try this. You can apply induction on n, the size of the matrices, and make sure you use this exercise. Exercise 6 from section 6.4. Let us now see the next one. If you want to search this result now, you look for this. Simultaneous diagonalization of commuting matrices. This fact in fact is true for not just two matrices but a set of mutually commuting matrices as well. Okay, so you look for this. In number 20, we have to prove that if we have diagonalizable matrices, but say we drop the commuting property, it's no longer a hypothesis. You have two diagonalizable matrices A and B which do not commute. Then it's not necessary that such a C can be found. So we have to now provide two such matrices for which such a C cannot be found. So let's do this one. Luckily, 2 by 2 examples exist. So we won't have to do long calculations. Consider these two matrices. Okay. Well, this 1, 0, 2, these are not necessarily real numbers. You know what 1 and 0 are in any field. 0 is the zero element, 1 is the unit element. What is 2? 2 is just 1 plus 1, that's it. That's what it is. Okay, so in that sense, we have these two matrices. B already itself is a diagonal matrix, so obviously it's diagonalizable. But just for the sake of definition, you can take for our B here F equal to the 2 by 2 identity matrix 1 0 0 1. So then this is just B which is diagonal, so B is diagonalizable. Why is A diagonalizable? For that we note this. Let us consider this conjugate 0 1 1 minus 1. I have it with me. A 0 1 1 minus 1 inverse. Let us see what we get from this. So let's first write what A is, that way it will be easier for us to actually do the multiplication. So A is 1 1 0 2, and the inverse of this matrix, it turns out, is 1 1 1 0. You can see for yourself. I mean, if you do the multiplication of this matrix and this matrix, what do you get? Let us use both of our hands to do this. You know how. First row times first column. 0 times 1 is 0, plus 1 times 1 is 1. Then first row times second column. 0 times 1 is 0, plus 1 times 0 is 0. Then second row first column. 1 times 1 is 1, minus 1 times 1 is minus 1, and 1 and minus 1 give us 0. Then second row second column, 1 times 1 is 1, plus minus 1 times 0 is 0, that means 1. So you are getting the 2 by 2 identity matrix. So yes, this is the inverse of this. Okay. So let us first multiply these two. So what shall we get? 0 plus 0, 0. 0 plus 2, 2. 1 plus 0, 1. 1 minus 2, minus 1. Then 0 plus 2, 2. 0 plus 0, 0. 1 minus 1, 0. 1 plus 0, 1. So you see that you are getting a diagonal matrix. That means yes, A is diagonalizable. Also, they do not commute. AB is not equal to BA. The verification of that I am leaving to you. After calculating AB and BA, you will see that they are not equal. So then you can write AB is not equal to BA. So we now have a pair of diagonalizable non-commuting matrices. Our job now is to show that there is no such C which will simultaneously diagonalize A and B. But forcefully we are going to suppose that there is such a C, and then something will go wrong. Suppose there exists an and that too not just any C but an invertible C. Let me write there. Because we will actually have to calculate, we will take the entries as well. This is capital C, this is small c, okay. In F2, such that, okay, now there are two possibilities. Let me write, you will see what that means. C is C inverse either C is C inverse is 1002, which is also CBC inverse, or CSC inverse is 2001 and CBC inverse is 1002. A question immediately arises. We just want these conjugates, CSC inverse and CBC inverse, to be diagonal matrices. Why specifically this diagonal matrix, or say this diagonal matrix? Why 1 and 2? Well, let's look at the matrices A and B themselves. A is what? A is 1102. A is what? What type of matrix is A? A is a triangular matrix, and in a previous exercise we proved that the eigenvalues of a triangular matrix appear on its leading diagonal. So that means the eigenvalues of A are 1 and 2. And that is why when you diagonalize, you are going to get the eigenvalues. So either it will be 1 and 2 like this, or the order may be changed like this. And since B itself is diagonal, so obviously, I mean, you can either have this or it's, in the reverse order, which we have not written. I mean, in these two possibilities, everything has been accounted for. Either they end up being the same matrix, or they are nearly the same, only the order of the diagonal elements is changed. Alright, now what can possibly go wrong from this? Let us see. You may also notice that we did not really have to do anything to show that A is diagonalizable. I mean, we showed that a specific conjugate of A by that matrix is a diagonal matrix. You just have to note that it has two distinct characteristic roots. I said eigenvalue a moment ago, no? Characteristic roots. Does that automatically say that that it is diagonalizable? Think about it. Okay. Alright, now what will happen if we consider the first case? If the first case is true, then CSC inverse is equal to CBC inverse. Now, because C is invertible, you can pre-multiply both sides by C inverse. That will get you, that will just simply make C vanish. And you can post multiply That means multiply from the right side on both sides by C. Then C inverse will vanish and you will have A equal to B. Which is not true. That means this cannot happen. So the only possibility now is this. So we must have this, that CAC inverse equals this and CBC inverse equals this. That is, transferring the C inverses to the other side, you then get this. Let us first see what we get from the first equality. Now what is CA? We are going to calculate that first. ABCD times 1102. A times 1 is A plus B times 0 is 0. That means A. A plus 2B. C plus 0. C. C plus 2D. And what about that side? One zero 02 times C A plus 0 A, B plus 0 B, 0 plus 2C 2C, 0 plus 2D 2D. And these two are equal. That means all the corresponding entries have to be equal. A is already, we have the same thing here. A plus 2B has to be equal to B. And C has to be equal to 2C and also 2C plus 2D. Let's just write all the non-trivial equalities. Thus, we won't write A equal to A, but we will write the other things. A plus 2B equals B, C equals 2C and C plus 2D equals 2D. And from these things, what do we get? We get that A and B are in minuses of each other. That is, their sum is 0. These imply that, let me write it like this, B equals minus A from the first equation. From the second one as well as from the third one, we also get that C is 0. So the matrix C itself now has been made more simple. So C now looks like this. A in place of B you write minus A, C is 0 and D, well, that is just D. And now we go to that second equation. Second equation means this one. And now we calculate CB and this times C with this C, with this new information. Next, CB. So C is this matrix A minus A 0 D, and what is B? B is that diagonal matrix 1 0 0 2. A plus 0 A, 0 minus 2A minus 2A, 0 plus 0 0, 0 plus 2D 2D, and 2 0 0 1 C. Alright, 2A plus 0, 2A, minus 2A plus 0, minus 2A. So here also we are getting minus 2A. 0 plus 0, 0. 0 plus D, D. Now this one will be equal to that one. So A equals 2A. What else? Minus 2A, same thing. 0 is present there also. 2D equals D. And this gives us the new information that A and D are both 0. But then what happens to our C? The C is the 2 by 2 0 matrix. But that is not possible. Why? Because according to us, C has to be invertible, and the 0 matrix of course is not invertible. This is a contradiction since C should be invertible. And that is why the forceful supposition that there is such a matrix C leads to this contradiction. So our A and D, although they are diagonalizable, cannot be diagonalized simultaneously because they do not commute. Okay, so with that, this exercise that is over. And we can then start the next section, next Saturday, where we have rational canonical form. Do you remember that in this Jordan form, we assumed that all the characteristic roots of our linear operators lie in the underlying field? In rational form, that won't be necessarily true. So it will be more complicated there. But still, results are available there also. So we will see what they are. And tomorrow, as usual, we have our analysis. And I think we have already recently completed one section on the two fundamental theorems of calculus. So tomorrow we are going to solve the exercises. There are only 3 exercises, one of which we have already solved, which is the proof of that antiderivative lemma. There are 2 more. So tomorrow we will solve those 2. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.